Grand finale, we are going to find limits to infinity and beyond. Hee. Okay, well, we're finding limits to infinity or negative infinity, and ultimately we are just understanding its end behavior. You know, what's happening as x approaches infinity. What happens as x approaches negative infinity, right? That's end behavior. You know, remember when we talked about polynomials, we were just looking at the degree and the leading coefficient, but now, you know, we might not just have polynomials, such as in this case. So, it says evaluate the limit as x approaches infinity of 7 minus 3 over x squared. So again, what's different is now that we have x approaches infinity, or in some of the problems, negative infinity. So, let's have you guys try this, think about it. If you're totally unsure, then go ahead, put me on pause, and then we'll talk about it. So, go ahead and try. You could also graph it to understand what's happening as x approaches infinity. Okay. Excited? Okay, if you have to use the restroom, go ahead and use the restroom, but there are 3 ways to do this problem, and I'm going to show you all of them. Okay, so first and foremost, one way I could use is this difference property of limits. So I could take the limit of 7 minus the limit of 7, or 3 over x squared. The limit of 7 as x approaches infinity is always going to be 7. But this, remember, we just talked about some of these properties. If I have 3 divided by, and I'm plugging in infinitely large values of x, this is going to go towards 0. So that's why this limit equals 7. Okay, another way to do this. Another way would be for me to get a common denominator, which I did, and then since we have even degrees in the numerator and denominator, I know that there's a horizontal asymptote at the quotient of the leading coefficients, which is 7, which also makes me understand that as x approaches infinity, this limit is 7. Then the third way, oh my gosh, keeping it together over there, the third way, and this is a way that we are going to use in future problems, is if I divide, so now using this form, if I divide the rational, every term in the rational by the highest degree term in the denominator, which is just x squared in this case, I do that, so I'm dividing everything by x squared, and then I simplify, I get 7 minus 3 over x squared over 1. Well, I know that this limit will go to 0, so I get 7 over 1, which is 7. Crazy. Okay, let's take a look at these 3 examples. So I'd like you guys to just go ahead and try all 3 while you're at it, and then we'll talk about them. Okay, if there's some that you're unsure about, just try to get as far as you can. So for this first one, the first thing I said was, okay, well, can I use direct substitution? But then I get this negative infinity over infinity, and we know that that's indeterminate form, so not going to work. Next thing I looked at is, okay, well, is there a horizontal asymptote? And since the degree of the numerator is less than the degree of the denominator, we know that we have a horizontal asymptote at y equals 0. Therefore, the limit is 0. Don't believe me? Go ahead and graph it. Same thing here. You know, I could do the whole direct substitution. I'd get indeterminate form. So look at my horizontal asymptote. The degrees are equal in the numerator and denominator, so the horizontal asymptote is negative 1/5. Now, in this one, since the degree of the numerator is 1 larger than the degree of the denominator, we know that we have an oblique asymptote, or in other words, a slant asymptote. So this is where I use that third method that I had used in the very first example, where, remember, we can divide every term in the numerator and denominator by the highest degree term in the denominator. So in other words, I just went ahead and I divided every term by x squared. You're probably thinking, oh, why'd you do that? That was dumb. Well, it wasn't dumb, first of all. If I simplify this, I get negative x plus 4 over x squared over 5 plus 2 over x squared. Well, when I take the limits of these two, these are going to go to 0, right? And then if I use the idea of direct substitution, and I plug in negative infinity, so I get negative the opposite infinity over 5, this will be a limit of infinity. Another way we could have done this also was we could have figured out what is the oblique asymptote by using long division, and then look at its slope. So that was another option. Okay, these two examples. So we are going to evaluate these limits. You guys could try these. The thing that's going to be complicated is that we have these absolute values, but that's okay. You could still do it. So go ahead, put me on pause. Okay, let's take a look here. So, first and foremost, let's just point out the obvious that if I use direct substitution and plugged in 4, this would be undefined. Okay? We all identify that that's true. So what I started doing was I started by factoring. Now, immediately we're probably tempted to cancel out this x minus 4 over absolute value of x minus 4. I mean, they're essentially the same thing, but they're not exactly the same thing. So we can't do that. You know, these two terms here would reduce together to be either positive 1 or negative 1. But we can't just let it go away. So at the end here, this is going to have to do with the sign of our answer, and what's left is this x plus 4, so it's going to be 4 plus 4. So now we got to figure out, is it positive 8 or negative 8? So, like we did before, since we're approaching 4 from the left, I'm plugging in values that are slightly less than 4. So 3.99 I chose. And when I do that, I get a positive times a negative over a positive, which means that this will reduce to a negative 1. Negative 1 times 4 plus 4 is negative 8. Now, in this next problem, notice that we're just looking for the limit as x approaches 4. In order for this to exist, we need to figure out what the limit as x approaches 4 from the right is. So that's what I did here. Same process. I plugged in values that are slightly greater than 4, so I plugged in 4.1. I got a positive times a positive over a positive. So this, even though that they're not exactly the same, I know that these would reduce to positive 1. So 4 plus 4 is going to be positive 8. Since these two are not equal, this limit does not exist. Okay. Evaluating limit results in a positive or negative infinity. That is called a descriptive limit. The actual limit doesn't exist. That's why we call it a descriptive limit. When evaluating a limit as x goes to positive or negative infinity, we want to think about end behavior. So think about asymptotes.